Hi everyone, so I'm Katherine Chimenes. I'm a structural engineer with Price & Myers. So who are Price & Myers? Good question. These are some projects we do. So we're a structural engineering firm. We're based in London. We have some companies across the UK. And these are some of the projects that we do. So it's a really broad range. We do things like satellite testing facilities down to temporary artwork. There was one picture, actually, I missed it, I should have put it last, but earlier we were talking about AR, so one of the tiling on one of the roofs, we asked the contractor to use AR to ensure the placement of the tiles match the ones we design right now. But we're structural engineers, so different caps. And that goes on to this topic. So I think a lot of people here are either in architecture or engineering, some are developers. And very often we hear about these computational groups, like these specialist research groups where you have people who are really enthusiastic about digital things and hack away and create the scripts. And actually I have some background in computer science. I started off actually doing computer science in 2010 at Imperial and went the wrong way. So I went to civil engineering to do structures. And the reason for it is because I really wanted to make things physical in the real world. And so I kind of carried that philosophy through. At the start, I was trying really hard to push everyone to script to learn how to code when I was back at Arup. And I really quickly gave up because I realized that it's not really the right audience for it. And I understand why you have digital specialists and computational designers in architecture and engineering. But with Price & Myers, what I tried to push there as a computational computational group leader, I try to find opportunities to see where we can automate things on projects we do daily with everyone on board. So with normies, as Jonathan called them earlier. And funnily enough, I just sit people down. So we've got 1 or 2 people, or sometimes more per group. So we've got about 12, 13 groups of structural engineers and 1 of civil in our company. And these people, we gather them around. So I gathered them around quite early on when I joined the firm. And I was like, OK, let's do a workshop. Let's brainstorm this. And it's a people thing, right? We're developing tools for people to use. So I asked them the question. I did this very silly graph that is backed up with 0 evidence. But essentially, the idea is that there is this notion of this curve that I came up with. And this line, so ROI, return on investment. So you're thinking about how much effort or time or resources I put into developing something and how much benefit do I reap from it on a project, right? So I'll give you some examples. So that was like a really quick fire, like you've got 5 minutes, I want you to write down like 10 or 20 ideas, design tasks that we have. And then, and we will opportunities for digital tools, automation workflows ideas, like things we do daily on projects all the time, and just stick it on where you think it sits on that curve. And then we put like red dots. I don't know if you're in London, there's like the Royal Academy like summer exhibition where you like put red dots on things you like. To buy them, to buy art, tangent. Okay. But the big problem here is adoption, right? So last night when we were having dinner, I was like chatting to a few people on email and I was like, should I mention it? I'll mention it. We're talking about like the tiramisu dessert. And it was like, no matter how good the tiramisu is, if you don't have a spoon to eat it, what's the point? Right? So the whole point here is adoption. So you can have the fanciest, coolest digital tools that can do all the best things. If no one can use it, what's the point? So this is the graph. And so the idea is that, this is like entirely theoretical. Bear with me. So you've got this line as well. So it's like we're trying to push for things that go beyond that line, right? That basically makes sense to use on your project. So you invest a little and you get a lot back. So it's the differential. And here's an example. So I want to create a spreadsheet to design a single member. That's already been done, but I want to do my own spreadsheet because then I can check it and I know what I'm doing and it's right. So I'll be somewhere here. And someone's like, oh, but what if I script it? because I know how to like do Python, and then it'll be better because then I can roll it out more easily. It's more easily scalable with like some API from an FE software, and I can like feed it lots and lots of members. But then, realistically, how many people in your company is going to use the spreadsheet versus how many people are going to use the script, right? So maybe it's not worth it. And do we ask ourselves that question? It's a question to you. And then, so yes, so this is what I mean. So, and you've got a greater risk of less adoption, so you're making a loss there, even though the tool might be amazing. And these are some of the like completely theoretical examples again, but it's a good question to ask ourselves. Like, why do we not try and automate the design of the whole building? Because maybe it's requiring too much investment, right? And we need to be conscious, like, so I work on projects. I'm not a computational designer full time. I try and spend a lot of my time doing projects because this is what I care the most about. I want to design things, I do structural engineering, I want to see things getting built. But this means that I want to think about these questions and help the whole firm and the whole industry ask these right questions about why we're doing these things we're doing. And then another thing is entirely cultural again. So you've got these computational groups in different companies, right? What's the issue? Okay, some people say it's an interest. Some people say, oh yeah, I spent a whole weekend writing the script that does this. It's amazing. Oh no, you shouldn't be doing this in your weekend. It's not a hobby. It's your job. You should get paid for it, right? Then it's too time-consuming and hard to adopt. A lot of people are like, I don't know how to use Grasshopper. I don't know how to open Dynamo. I don't know how to read code. I can't check your work. I can't, like, you're giving me a black box. I don't know how to use this. Then, like, I've seen so many engineers just leave, or architects and go work in tech because they pay like 10 times more. And then, it's really hard to quantify as well. Like, how many of you have tonight presented real hard numbers? Where are your KPIs? Like actual monetary figures of how much money you've saved your company or how much time you've saved your company. And lack of recognition. Like, you have a lot of senior management who don't actually understand what we enthusiasts in this room do. How do we get recognized for it? And you've seen our peers earlier showing like all these slides and graphs and trying to like explain to people like what we're trying to achieve. So we're not recognized because, once again, the audience doesn't get it. So culture shift, that's what we need. Another thing again, this is what I want to talk about. Right? I'm a structural engineer. I want to think about how we design things. But instead, we're spending our whole time trying to think, how do we coordinate our design model? Like, this whole conference is about this. It's about data. It's not about designing a better world. It's about how we deal with data. Like, what are we doing here? And once again, like, you think about a building design. Lots of parties, right? We don't even have like 80% of the people on here in this room. That's also a problem. When we talk about total design, integrated design, not everyone's part of the conversation. That's another problem again. So many problems. Okay, and more problems. So the whole, sorry, just a spoiler alert. First half is just problems. And then it'll get better. We save data in different places. There's way more. It's like some kind of like highlight of like my daily life and what I encounter, and you can see like versions. You've got like final, real final, v14. And it just goes on and on and on. And then what do you have next? You've got models, other models, drawings, existing drawings, like sometimes physical drawings. Like currently on my floor in the office, there's a stack of tracing A0 sheets of drawings that people go and ruffle through, and it's really loud and annoying. And like, this is reality, especially if we're moving towards more sustainable design. We're going to have to deal with existing buildings and go through those archive drawings. There's no way around that, right? The data is unclean. That's probably what's saving us from AI taking over, is because our data is so miscellaneous and unclean that you can't apply machine learning on it. Hooray! Yeah, so 3 themes here again, when you look at all these like really high-level concepts that we deal with in the entire industry. Version control, coordination, QA, quality assurance, checking, right? So I'm going to tell you another story now, a case study, not with Speckle, but it's going to explain to you how my thinking kind of grew from this experience. So this is a project, so I got given this. They're like, okay, fine, artist shows me that. Great, make it work. Okay, what do you mean? Make it hang in the air, outside. Okay, fine. And what we do at Price & Myers, which is quite interesting, is that we have quite a strong cohort of computational designers that we're not called computational designers. We're just structural engineers who are good with scripting, Grasshopper, Python, like all the stuff, you know, like, yes. And the idea is that a lot of us deal with artists and art, because art requires unusual materials. You have to work in 3D, and you have to think back to first principles and rethink how you do engineering. You don't have all the Eurocodes to fall back on. You don't have all of the like standardized methods of designing things. You have to actually scratch your head and solve a problem from scratch. But that enables you because, firstly, it's very short term, usually. And it means that you have more fluidity. Because you don't have those constraints, you can start and build something new. It's a bit like when you compare the construction industry with the tech industry. The tech industry is a lot younger. It could build things from scratch, the ways it works, right? Compared to the building industry where you've got all these processes in place that have been around for decades. The tech industry just goes in and says, hey, why don't we try this way of doing things? And this is what we do and the mentality we use to approach the design of art projects. So you think, an artwork, right? How bad could it be? Well, these are all some, not all, of the models and data that I had to take into account for the design of this one artwork. Okay, so we're talking about like this new building that I recently completed was still under construction when I landed on this art project on this public art program. So it's the Paddington building, the Cube by Renzo Piano in West London. So you've got, for example, like really absurd things. You've got an invisible boundary line that divides the new building, and half of it, or like 80% of it, is modeled in Revit, and the other bit is modeled in Navisworks. And there's no join model, okay? And I'm just coming in, I have to suspend this artwork using all the structure I have, and of course it had to be set on the boundary line. And then you've got numerical data, you've got like a lot of different kind of, you know, data. The artist's geometry was so poor, it wasn't even a mesh, it was just a set of lines that didn't meet, right? So it's like, it's just, anyway. So much trauma and PTSD. So structural challenges. So, okay, this is where they want it to be. You've got this existing slab, edge, a hole. The blue things are escalators. How am I going to hang this, right? Yeah, so all these constraints. Just to give you some background, this is how it looks like. You can see huge hole. So it's windowed. So initially what happened is, so first I had to get all that information, right? Compile it somehow. So I compile it all and I put it in my favorite software right now. But it took a huge amount of time. And then every time something changes, it's like conversion, trying to put it in the right place, rotating it 90 degrees because it was imported from a step file and it's not like, you know the deal. And then in reality, the story is we started off as Czech engineers. So we had the fabricator who's already worked with these artists and his German structural engineers who worked on this. And we were trying to help them and say, okay, why don't we like nudge you in the right direction? Because I don't think 44 cables like this with zero pre-stress when it's going slack all over the place is really the right answer. And they were like, yeah, actually it doesn't work. It doesn't work. We need to put a 10 centimeter diameter column down the middle of the artwork, option one. And I'm serious, like they presented that to the whole design team, client, artists, architects, everyone. Or we can put a glass box around it. Like these were the two options, plus the 44 cables, of course. Don't forget that. And this is what we have to deal with. So clean up the mesh, rebuilt the mesh actually, then came up with a finite element analysis model for it. with pre-stress, and it was a nonlinear model. I won't bore you with the technical stuff. We can talk about technical stuff after, and cycling, of course. And the idea is like you have one model per win load case because every single model took 18 hours to run. And that's the fabricators model that we had to work in conjunction with because it wasn't just a matter of, okay, this is the design, size it. Because it's nonlinear and we have large deformations, it was, okay, depending on the placement of the bottom connections, everything's going to move. We have to rerun the analysis and the force is going to change and the way the connections design is going to change. Because you have a cat cradle system here, we can't like tie it down to the ground, so we have these slab edges, and the idea is that the bottom will stiffen it up to pretend and imitate a very stiff bottom support for a vertical rod, so that when the wind blows, that rod doesn't go like whee, it goes like bing. The right one is in plan, right? Okay, so I'm going to fast forward because this is not what I'm trying to explain. This is like physics engineering kangaroo. But the whole point here, notice I'm only talking about engineering here. But the underlying text here is all the software and the data exchanges that I'm dealing with, right? So play that background story in your head. I don't want to do like full American TV crime series exposition. You're all seeing what I'm getting to here. But this is the engineering, and this is all the data transfer I'm doing in the background. Yep, and what I mean by things changing, like I spent weeks getting data from different parties, including like the facade, the stone cladding engineers from Italy. And they're like, okay, these brackets are here, this is the exclusion zone, you only have this space here, this is an upstand, so actually the thickness of the slab only stops here. So it's like really tight, and we're dealing with really quite large forces here, like over 180 kilonewtons pulling out, and it's not just tension, like normal out of the face of the concrete, it's actually dealing with shears at an angle. And then when I say, if you move that a bit, right, so the way the rods like are positioned, they have to meet at points where the vertical rods hit the steel canopy. So if you move that like by 100 mil, that plate there, I hope it's coming soon. No, it's not. Sorry. That vector is going to change. When that vector moves, that plate's going to change. I have to redo the analysis in my FE software. I have to rerun the global model. Okay, and once again, think about all the underlying like data exchange. Yep. So this is me in Grasshopper and Rhino trying to create a workflow, speaking with GISA, which is the finite element software, being able to update this constantly. Yep. And that's the actual model that's created from the thing you saw just now. So cladding model, rivet model, and that's just for the bottom connections, reactions from FE models, new connections for new model, blah, 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 blah. Like, so much time. So much time. I don't call this engineering. I call this data transfer and cleaning. Yep. Same thing. That's just called waiting for inappropriate software to run. Yep. And that's, in reality, one day to pre-stress it with strain gauges, like crappiest software. Like that computer crashed, the guy was sweating because he was like, I'm getting paid to produce that graph for you, and it crashed and I can't save it, and if I don't have that graph, I won't get paid because contractually that's what I'm issuing. That is like the opposite of Speckle, right? It's like, it's things, it's so old school, but this is engineering. These are strain gauges, and we're trying to make something work, not because I like spend time like sliding sliders on Grasshopper to make something look parametric. I was given a set of constraints, and I wanted to make something better than a 10 centimeter diameter column with a glass box and 44 cables. And that's the end result, okay? So this is, I'm driving here at the forefront with structural engineering design and creativity and problem solving. 4 years for one artwork with everyone, including my boss, being like, it's never gonna get built. It's never gonna get built. And 10,000 plus files with 97 gigabyte of files? Like, what are they? None of them are videos. Like, what is it? And you can see the rods here. And it's just also, like talking about structural engineering. Again, numbers, nothing to do with like tech or anything. But the strains and the rods landed 10% within what I designed for it to be like vertical rod straight and then everything in tension and balance. Yeah, 10%. And before we pre-stressed it in one day, No one, including people on site, believed it would work because everything was bending. And they still didn't understand the concept of pre-stressing, but it's like a cat's cradle. I tensed it, and then there you go. Now, all of this is to explain that I believe that all of these things should be one. A structural engineer should have those skills, but it shouldn't, the driver and all these tools shouldn't be the things that we shout the loudest about. They should enable us to do good engineering. So I took this 4 years of hard-learned lesson and I brought it on this project. And that's very interesting. So Arts and Culture Center in North Wales. Yep, architects who at the start of stage 4 were like, let's scrap the whole design and do something entirely different. Let's go from CLT and do something that is wacky geometric roofs and softwood timber. What can you do? You can drive the geometry, but do something protruded so it can like echo the rocks of Anglesey. Early stage 4, so really, really tight time, no budget, you know, the whole shebang. And then, okay, learn from the lesson from the artwork. Scope, and I think some of the earlier presenters talked about this. Who's responsible for what? So we're going to say, okay, architects are responsible for setting out. We're going to do connection design, but we're just going to do these blobs. And then the fabricators are going to do a geometric coordination, steel and timber fabricators, to understand how to make the geometry work and not clash. But we're only going to, and we drove this, so we actually picked the steel fabricator to be on this job, and we actively relinquished the responsibility of doing the 3D modeling of the timber and the steel nodes because we knew that that had to be part of one party's package. Yep. It's not about, I can do this, so I'll do it. It's what makes sense. They would devise this document. What is this document? So I'm really sorry. Can I have some water? Sorry. Just someone, please. Speckle connectors, the top thing is, okay, this is how you install it, this is how you set up connector. And then a very simple thing, like how do we name our folders and model, like, what do you call it, like branches, yeah, and models. That's all I needed. And then I'm so sorry. Okay, and we're talking about architects here who have not really worked in 3D. They had like a SketchUp license, like for the whole company, and they tried to like model something. They like mainly drew in 2D, and I was like, okay, I'm not gonna be like, hey, please get onto Rhino. Like, we don't have time. How am I gonna like, who's gonna train them? You know, how am I gonna do this? So we used Speckle. And what does that mean? So we had these drawings. We did these drawings still. And then we essentially did our 3D modeling and put it on Speckle and shared a Speckle link, right? And we're like, okay, look at this. And the architects looked at it and they're like, they started asking questions they couldn't ask before because they didn't see it in 3D. So it was like, oh, hey, this is easy to use. I can see what's happening. And that's what happened. So luckily, the fabricators knew how to work in 3D, so they modeled something in 3D. And then in a weird, bizarre way, it went backwards. So the architects looked at this and started leaving comments, and they added their lovely sketches, like doodles. Oh, yeah, so it's like, you can see like a polyline. This is the other one, I should have included that. It was like a hand-drawn sketch with like a photo on a phone camera. But the whole idea is like, it's not about tech, right? Once again, the whole point here is we're trying to design something. So we got them on board. And the greatest thing is that it all just, followed through. So we could comment on things. So I was away on holiday for a week, and my boss was like, oh, we need to check this for approval. He just went onto Speckle and looked at this. And I mean, it's as simple as that. So we had a color code. I did a color code thing for purple was 4 bolts, orange was 6 bolts, and yellow was 8 bolts. And you just go into Speckle and you're like, purple 4, check. Like it's literally as simple as that. And the thing is, all the fabrication drawings were generated with the script, not by us, by the fabricators, off of that model. But everything was in there. And same thing with version controlling. So the whole idea is like, when I was showing earlier with all the different file names, you've got loads of files saved and you can't remember which is the last one. And on the previous artwork, it was a whole nightmare. Whereas here, like, I don't even need to save stuff. I just open Rhino, I click on the Speckle interface, and I go on the project that I want, the build that I want, and I say latest version. And we have like one branch for different parties. So if I want that model, then I'll get it. And I know it's the last one. Like, I'm not wasting time. I get the time to do the engineering thinking. Yep. And then it goes on. So they did 3 buildings with the same process. And I'm talking about people who didn't even know what Speckle was. And architects who didn't work in 3D. But they all got on board. There was no risk. I didn't feel like I was at risk because it was simple. It did what it did on a TIM. They ended up using Rhino. They ended up learning how to use Rhino because they realized they had a need to learn how to use Rhino. Or work in 3D with any other software. And then the beautiful thing is we did a whole other part of the extension in Revit, the standard way, with drawings, and then we could just import it with Speckle, the 3 wackier buildings into it, and it just updates our drawings. So it's, different software have different strengths for different purposes. And then you can put it back on Speckle again, and then you can give it to the client and you can spin around. And actually, we use that same, I'll show you in a bit. So that same model was used for fabrication. So the fabricators created that, put it on Speckle as well. And then, so fabricators, oh, whoa. Hurry. Where's the button? Help! Hey, thank you. So fabricators, structural engineers, I can't remember what I was saying, so I'm just reading what's on the slides. Architects. Oh yes, so the architects actually just bought into it and designed all the other elements that you need to design for the build-up in here. They were highly geometric, some of it. And they didn't have to use Grasshopper for it. It was just a matter of, okay, you've got to do it, find a way to do it. And they learned how to do it in Rhino. And they were like, oh, can we do this faster, like using Grasshopper? And I was like, yeah, sure. But I'm not going to teach you. And it's probably faster to do it by hand. See, it's not about like how shiny the tool is. Sometimes it's just about getting stuff done. And there you go, on site. And it just fit because we worked with the right people, we knew what the constraints were, and talking about like fitting things together, we knew the steel fabricators had a capacity of welding those nodes with that geometric accuracy. Yeah, it's about understanding like having jigs and procedures in place and the experience of knowing how to work with geometrically challenging pieces. And then we also knew how to guide the contractor who have never worked on something geometrically so unusual to deal with it on site. So like temporary cases, we just put straps around the columns so they wouldn't splay out without having the arches spanning the whole way. Like really simple, low-tech stuff, like ratchet straps. Yep. And that's just more shots. And that's another building that literally got put together, I think, in the past month or two, and that's the Speckle view. And you can see it's just pretty cool to see how they align. So just a quick recap, nearly there. So centerline model, architects, right? Analysis model, we use Excel. I could script it. Just think about the curve I showed at first. Didn't see the point. It was very bespoke. Did the job. 3D geometry model, so that's the one the fabricators made from our information. So we get in the center lines, get in our sketches that we did in Bluebeam, like super low tech. Did some comments. We did a 2D element analysis model that I didn't show. I had nodes in 3D actually. So we took the information from the fabricators and then modeled those nodes in 3D and merged that with our 1D finite element analysis model. And with Speckle, it just became this. Yep, so I got rid of the whole like, it was just like app.speckle, enter. Okay, spin, right comment, done. I mean, I have to say, it's pretty good. What it means is 6 months. Yeah, I won't even show file size because technically there's no real file size thing. It's on Speckle, literally. There wasn't an adoption period. It was just like, here's the PDF, let's have a call, let's do it. Oh, you just download it like this? Yes. I think like sometimes simpler things are taken for granted and they're what work best because you get most people to use it. And it didn't matter if some people used SketchUp or some people used 2D software or just AutoCAD or anything else. I don't even know what they used. I don't even know what the fabricators used. But does it really matter? Like, what I care about is what we design, what we make, what we build. It's not what tools have been used to get there. It shouldn't be the case. Like, we're losing sight of where we're trying to get to. But yeah, that's my take. Thanks. You can add me on LinkedIn here. I'm also trying to potentially down the line. I want to sort of get the conversation going online with people who share that belief. And the idea is that we don't have all these like silos of digital enthusiasts and the rest. We're all one. So reach out if you want to talk about it. Great. Thank you.
So wait, you're not taking questions?
Oh, okay. Questions, yeah.
Sorry. Probably a few, I'm sure. Thank you, Katherine, for the amazing energy. Exactly what we needed at 5 p.m. Anyone? There must be one. There you go. Joost.
Thank you, Cinda. I have a very short one. Oh, that's a bit loud. The curve you showed, what's the pink curve actually?
The pink one. Oh,
Yeah.
The pink one is like the trend. The trend. Should I put it, wait. So like, it's, once again, it's theoretical. You know like the stuff like BCG and McKinsey do for a lot of money and that don't really make any sense? Like that's me trying to do that for free. So please be kind.
Okay. Fantastic. All right.
But the whole idea is, okay. So essentially my theory, but also, so my theory is that that's a trend curve for all the design tasks that you can create, whether you're automating it or doing it manually.
Like
so
usually you're on that line.
Huh?
Usually you're on that line.
You're not, yeah, you're like it's a trend line, right? So
Yeah,
it's like
okay,
that, yeah.
Okay.
So the whole idea is like, okay, I'll sort of like walk you through it. So if you start doing something with little, like very, very minimal effort and investment, it's probably not gonna be very like good in terms of return. Yep, if you put a little bit more investment and say, okay, I'm gonna think about how I can improve it slightly so it can be reused, for example, it starts going that way. So the more resources you throw at it, the more investment you throw at a task and how you do the task and create the design task, whether it's automation or something, it starts going up. But then at some point it will dip. So there's a tipping point where when you invest too much, yeah, it's diminishing returns.
Yeah. Okay.
That's literally it.
Okay, great, fantastic.
Does that make sense?
Yes, it does.
Okay,
And
cool.
the whole presentation also. It was great.
I'm so glad people like think it makes sense.